Today I'll talk about long-range telecommunication in the HF band, more specifically about civil solutions for HF band telecommunications. Um, I work for Rhizomedica, and this project is called Hermes, High Frequency Emergency and Rural Multimedia Exchange System. And this is the logo of our project. And I'll start showing the radio first, that I think it's one of the most interesting things we did the last years. Uh, this is our equipment that has a HF radio, a computer inside. And with this, there's also a Wi-Fi antenna here. And with this radio, you can connect, for example, an isolated community in the Amazon rainforest. That's the main place we work right now. To another place that can be very far away, many hundreds of kilometers, and make a link between this community and another station, um, usually a station that has internet connection, so the data can be routed to the public internet. Um, this is the back of the radio. There is a HF antenna connector. Like in Brazil, we call this connector UHF, but I think the name is PL259. Please correct me if I'm wrong. Also here in the back, there's the 12 volts input, GPS antenna, and a Wi-Fi antenna, and an Ethernet port. And this is the back of the radio. And now it starts the presentation. I just wanted to show a bit the equipment we did, and we are setting up in some places already. So why HF band telecommunication is important, and first of all, how it's defined, right? The HF band is defined by ITU. More recently, I mean, the 20th century, this definition is more or less recent. There's less than 80 years definition. And it's the band between 3 megahertz and 30 megahertz. This band is very special in a way because most of the signals inside this band, usually the lower part of it, bounces in the F region of the ionosphere, especially in the F region. And this means that you can bounce your signal, let's say, around from 100 kilometers up to 300 kilometers, and the signal will bounce back to the Earth. And then this is a one-hop signal, and then your signal can go up again and down again. This is a two-hop signal. And then you can virtually reach any part of the world. It was a main communication media to many places in the world, like, for example, from the metropolis to talk to their colonies, be it in Africa or in other places. In the 20th century, the HF band was used a lot. For example, the Brazilians heard the first Brazil World Cup in 1950 from shortwave AM radio. When I say shortwave is synonym to HF, okay, and most likely I use both the terms during my presentation, one or another. So yeah, it's the same. And so it was very important, of course, since the beginning of the artificial satellites in the 60s, its importance for civil telecommunication declined. Nevertheless, the military HF telecommunication systems continue developing. Of course, it's the most robust telecommunication system that exists on Earth. And so, of course, for the military, it's the last resort telecommunication medium. And of course, so because of this, very important, it's already in its 4G era. The first G is the analog telecom system from the 60s and 70s. In the 80s, they introduced the first digital telecom system that's called AO, Automatic Link Establishment, in a generic way. Then in the 2000s, there was the 3G era of the military HF standards. And then more recently, in 2018 or 19, there is a release of the fourth generation military systems that also call it wideband automatic link establishment. And here in the picture, it's just a small illustration of the ionosphere. The D region, E region during the night, there is just one F region during the day. The F region divides in F1 and F2. In high latitudes, in lower latitudes, it divides in F1, F2, and F3. Um, there are also a lot of small difference between the propagation close to the tropics, close to the equator line, especially because of the ionosphere anomaly of the Earth, and it's different than the poles, for example. Yeah, and also there's the 11-year solar cycle that there are highs and lows inside this 11-year, and this also changes a bit the propagation. Um, well, coming to the real world, this is one of our first deployments that we did in Brazil, in Pará State. Um, Here, 60 kilometers is this size. So, for example, these colored dots are the stations installed, and this is the central station. When there is internet telephony connection in Altamira, in Pará State, in the north of Brazil, in the middle of the Amazon rainforest. So here easily there are more than 250 kilometers, and to the more far away station more than 350 kilometers of distance. And here is we installing um, an antenna for the. I think this antenna was tuned in 6.2, something around 6.2 megahertz, 6,000, I think 6,200 something kilohertz. It's a simple dipole. We usually install like this, a simple dipole. There is here a balloon and inverted V. We like inverted V because it gives a more or less omnidirectional radiation pattern. So I mean, don't need to think about pointing the antenna and everything. Of course, there are billions, millions of types of HF antenna. I mean, ham radio people really love to design crazy antennas, but the simple one, the simple dipole works well. This is what we use. And well, okay, going already to the description of what we developed. Since the last time I talked a bit about Hermes in the Osmocom, we didn't have a hardware, and the software was very, let's say, young. And then we were basically connecting a computer to a HF radio, to a stock HF radio, and make it work. It was not really very successful because I think there is an HF radio here to show. Ah, here's HF. Usually HF radios that we use are meant for ham radio usage, and they have lots of buttons and whistles and bells for ham radio operator. But for a digital signal, what all these buttons can do is really harm the signal. So it's, I mean, if you touch the radio, you fuck up the transmission more or less. And usually the communities which use such system, they basically use the HF radio for voice, for analog voice, SSB. And when you connect a lot of things on it to transmit digital, it's not a very sustainable option. So we decided, okay, we need to build our own system that just has a power on and power off button. and the users can just connect to the Wi-Fi of the box and use for what they want, right? So we designed this box. This is the first version of our Hermes system that we are still using. In the left, you can see a very early prototype where the wires are just flowing around and it's a crazy mess. And then in the right, it's a little more organized box. We basically have inside this box the HF radio. That's this one that I just showed in the. Let me see if I have the board here. Yeah, this board. It's a Microbit X. It's a radio that is open hardware, developed by an Indian ham radio operator. It's called Ashar Farham. I'll talk a bit more about this radio. And we connect this radio to a computer. We have two audio cables going out and in of the radio. And we have a USB cable that connects the Arduino that does all the control of the radio to the PC. And also a Wi-Fi and this box indeed the GPS is not here, but we also added a GPS that's like hanging here, screwed here, and then it connects the PPS to one leg of the Arduino, and the USB also goes here for us to have precise clock in the PC and precise frequency synthesis by the radio. And yeah, and that's it. And I also talk a bit about the services that we provide that in the end is the most important for the users and of course um, to make it work and to provide meaningful services to the users. And well, so I said I will talk a bit more about the radio we use right now. We most likely will change soon to the SBTX. That is a new version from Ashar Farham. That then we will not need the audio cables hanging around. I can talk more about this radio later. But the one we use, and we are very successful on it, it's this small radio that we can get around 15 watts of output. And it uses a SI 5351 for the frequency synthesis. It indeed used the out 3 port from the SI 351, one for the BFO filter, one to give the center frequency, and another one for the BFO, one for the frequency, one for the filter, for the passband filter. It also use clock synthesizer here. So we don't use this radio stock. We do small modifications to it. As I said, we added a GPS to it. We add some LEDs in our box, like on-off LED and TX LED, connected LED, and high SCWR, alert LED that we all control using this same Arduino that comes with the radio. And we also added a lambda bridge to have measurements of forward and reflected power. And basically, these were the modifications. We also removed some stuff like the Morse modulator and stuff that's very tailored for ham radio. We removed to especially to free up some ports in the Arduino, and we also removed the screen. It used to have a screen in the radio. We don't use it, and yeah, it's very neat radio. It costs $130 just the board, and the fully assembled radio with a PTT that you can already use for voice communication or for Morse communications, like this $200, the full kit. You can see in this website. anyone interested. And going up in the network stack, we have the software-defined modem that we run on the computer. And right now we are using Vera. In the very past, we used AirDop. That was a free software modem, so the performance was very poor. And then we tested this Vara HF. That's a proprietary software, a Visual Basic 6 application that runs well on Wine. And so we run it inside the box. It has an adaptive modulation that can range from 16 bps up to 5 kilobits per second. And it supports 500 hertz BW, 2.3 kilohertz of bandwidth, and 2.7 kilohertz of bandwidth. We use 2.3. That is what our radio pass without distortion. Let's remember that all the HF radios are 3 kilohertz wide at most. They're made for SSB voice. So, I mean, all the standard HF radios usually have at most 3 kilohertz passband. So, yeah, this is a limitation. I'll talk more about this later. And of course, we want to have a fully free software solution. And right now, the only proprietary thing we are using is that Vara thing. So we are developing our own modem too, which will be able to use a flexible configuration of bandwidth, because we aim to be able to have wider wavelengths greater than 3 kilohertz. We expect to be able to use at least up to 20 or 20 something kilohertz soon. Of course, we need a bit more power, and we are working on it also. Well, this Mercury modem, it uses OFDM modulation with the LDPC error coding correction. Of course, there is also a channel estimator and other stuff that I don't understand much. It's another guy working on this modem called Fadi. His PhD is related to LDPC codes, and we are advancing, but we don't think before the end of the year we'll be able to substitute Vara with Mercury yet, because we still have to write all the gear shifting. The automatic repeat request is almost done, but define all the modes and the different robustness of all the modes to be used by the gear shifting, something that will take a bit of time. This is a comparison about the available modems for civil use. Let me see if I can get everything in the screen. So we are using Vara. That's this guy in orange. Here it's bytes per minute, and here's the signal to noise ratio. We usually have something when the channel is good, something between 5 and 10 dB of signal to noise ratio. So we can transmit something around, and this is true. We this this relates to the reality, like around 2 to 3 kilobytes per minute, with a uh, typical propagation channel in the 40 meters band, when you have distance between 0 and 600 kilometers. Yeah, this is what we get right now. So above the software modem, we have the UUCP, that I'd like to thank Harold for mentioning it in my last talk 5 years ago, 4 years ago, that we were using some stuff, very ad hoc stuff, and then Harold mentioned UUCP, and we adopted it. Very fits the need we had to have a protocol. store and forward protocol, asynchronous store and forward protocol, and UUCP fitted perfectly. So we are using UUCP. We have some caveats how we set the UUCP. The UUCP node name is the station call sign. So we use this for the modem to call another station. It uses the UCP node name. Of course, we use also alias in the UCP in order we can put a nicer name there. And we wrote a bridge that bridges UCP to the modem, and it's basically a daemon that's running like a UCPD, and this daemon keeps listening, always connected to the modem. If there is an incoming connection, it just gets the data and run UU cycle, and the other way around when the host want to initiate a connection, the host will call U cycle, and then the UCP will call this UU port command that will get the data from U cycle and insert in the daemon. This UU port connects to the daemon using shared memory, and this /z is a patch I did to UCP in order we can use the node name here as an argument to this UU port that I wrote. And it's already in Debian stable. So if you're using Debian stable UCP, it's already there. There's no more upstream UCP, right? I wrote to Ian Lance Taylor, and the last release is from 2001, I think. And he said, "Oh, there's no need for new releases." And okay, so I just pushed to Debian, and all good. And we use the Y protocol. That is a protocol that have no error correction, just asks for the packages, because indeed the modem is already a dump pipe, and all the data that comes out of it is correct. So the Y protocol seemed well and works well. And so going a bit up, and how do we organize all the mess inside the radio? We have a repository that's the Hermes net, and then we have the firmware, that's just the software that runs on the Arduino. We have a user land that talks to the radio, talks to this Arduino. And we have this UUCPD that makes the bridge between, that I just mentioned, that makes the bridge between the UUCP tools and the HF modem. I wrote this UUX comp of compression that basically is a UUX wrapper that I use in postfix to compress emails before enqueuing in the UUCP queue. And this UU comp also comes with the CR mail. That's just a R mail wrapper that just decompress the email in the other end and does some other magic there before sending the email ahead. And well, we have some folders with some scripts and init scripts and some scripts to list the UCP queue, some scripts to queue emails from the queue, some scripts to check how much data is in the queue, and if the queue is full, right? We cannot transfer much data over HF, so I limit the data that can be there. If there's too much data, just answer the email to the person, say, look, the queue is full, wait, your email was dropped. And yeah, this repository is basically the core of the network, part of the core, of course. And yeah, that's what we did to make it work, let's say like this. And then above this, we have a PHP API that we have the radio API, the user API, this user that's used both in the web administration page and also for the email accounts. The radio API, I mean, I have how to set and get frequency, set the mode, USB, LSB, set the BFO, that controls the circuitry that goes to that interferes in the end with the pass band, with the pass filter, the band pass filter that's inside the radio. We also control the offset of the PLL of the SI 5351. We get data like reflected forward and stuff like that. We also have a message API that is something different than the email. That's basically a message package that we put a JSON file, the message, some metadata, some attached files or stuff like that, and it's just basically a UUCP copy from one computer to the other. Very simple message exchange between hosts, right? We have a system API for basically system configuration and status report. We have some UUCP API to get the UCP jobs, also to start to use cycle that we call force connection in the UI. And in the and well, let me talk a bit about the network topology before I talk about this gateway API. Our networks use a star topology, right? There is a gateway station. That's a station that has internet, usually in the city, and then the remote stations that are spread in usually very small communities in the forest. And this gateway station has some added configurations. For example, to organize the schedule that this station will call the other stations. You can have different schedules, different time, and also the stations that the gateway will connect can be in different frequencies. So the gateway can set the frequency of the station, connect to it. I mean, just like in the past, it was the UCP dialer that you set the telephone that you want to dial for a computer. In our case, it's basically a frequency and the mode, right? USB or LSB of such station that the gateway will need to connect to synchronize the data, right? And we also have the web code. It's an Angular code that provides the web access to the system with all the configurations there, user management, radio administration, and this send and receive direct messages that are just UCP copies, and and what more is there? The scheduler in the gateway, or the set all the frequency of the remote stations in the gateway in case they are different of the default frequency. There is also a button to trigger the GPS calibration. That right now I don't do online calibration because I don't have free clocks in the SI 5351. We are redoing this board to have more clocks, but then all the clocks are above 10 megahertz, so I cannot read in the Arduino. So I just get one of the clocks, the one that is connected to the Arduino, and set a low frequency, do the calibration, and go back to working state. So we have a manual button to do GPS calibration, and we also have a cut threshold setting that above some reflected level, the radio shuts down. Not the radio, I mean the just the output of the radio cuts in order not to burn the finals. And yeah, this is what is in the web front end. Here are some examples of what really looks like. Um, so here there is the menu, messages, email, administration part, help, and to leave. If you click email here, you just go to a page that lets you choose a mail to address if you want to just send a mail directly, or to go to a web mail. And these messages is those messages I mentioned that are just UUCP host copies of files. And this is what looks like this message page. You can write the message. Here are the received messages, and you can see the sent messages. And here's what it looks like, the administrative interface of the radio specifically. You have the frequency, some measurements, serial number, and down in the page you can change all the settings, frequency, mode, and other parameters like the SWR cutoff. And here is the transmission list that we call in the UI. That's basically a listing of the UCP queue, and we parse it. Of course, we can show when it's an email. Here's an email to SMS at hermes.radio that I was doing some tests to make a bridge between email and SMS. And then this is just an email of 496 bytes. And yeah. And of course, one important part of our system is the email stack itself and all the setup that we did. Basically, each equipment that I showed the picture runs a full email stack, postfix, dovecot, and so on. The postfix code is UUX wrapper, as I already said. And then after the bank path, it calls rmail instead of crmail. I strip many headers of the email that are incredibly verbose. Didn't know the emails, like you send a hello over email and you get a 1 kilobyte email full of full of headers, like full of them. And just wipe them out, especially because the email is still in our network, so it doesn't matter. And right now, if you use a Delta chat or I even tested with Thunderbird. I think it works, but it works just with one attachment. And as Delta Chat just support one attachment per message, one audio or one image, we're, we're right now really recommending Delta Chat, not only for this reason, for many reasons, but and for the reason also we recommend, we support this special compression for Delta Chat messages. We get any audio Delta chat encodes in AAC. Then we convert to LPCnet to go over the air. Any image we convert to VVC using an algorithm that also does downsampling of the image. For the final image size gets around 10 kilobytes. And the audio LPCnet encodes at 1.6 kilobit per second. Pretty okay quality. And so as I mentioned, one station's we call Gateway, which has internet connection and can access our main email server in DigitalOcean that we use right now. And the remote stations just route the emails over UCP to this gateway station. Each remote station has a domain, right? So I have a postmap file that if the email is for one domain, I just route to that host, that UCP host. It's not very evolved yet. We still have some gaps to address. And yeah. Oh, I just saw a news message. It's Portuguese. Thanks, Harvard. Sorry, I should have put English screenshots. We have them. I don't know where I put in Portuguese. Anyway, I think you get it. And here's Delta Chat. Here's the Android version in the left. Here's the login. Basically, the only thing you need to do is create a user in the Hermes interface and put your login here, the email and the password, and it will already connect to the server. Good to remember that all the users are connected over Wi-Fi to the box, right? The Wi-Fi in the box running the access point mode. So people really connect to the box and can connect with the email. send pictures and everything. There is also some nice web applications that you can send in Delta Chat that are also very small, and you can play with it, and it show the score in the chat. And web XYXC, if I remember well, it's like a self-contained website, more or less, but can write to the message to the chat and do some interactive stuff that goes over email. That's interesting. Um, so I gave already an overview of the system. Of course, I could stay talking about it for many hours, but I think I'd like also to hear you and talk about you. So in the near future, what we'll have soon, we plan to substitute Vara by Mercury. Then we'll have 100% free software solution. We plan to have our wideband Hermes version that will be more than 3 kilohertz, hopefully around 20 kilohertz, maybe more. Of course, this is also painting regulation. We're in touch with Anatel and other regulatory bodies to be able to use it. I also did some tests with integration with SMS. There are still some loose ends that I need to fix, but it's working. I also implemented some data acquisition and transmission, uh, very small system that I get data from the charge controller, from the GPS, and send it over the air. I send the binary data. I compress with PAC8PX. That's one of the state-of-the-art data compressors that exist out there, and it really compresses data a lot. Takes a lot of memory, but really is worth, like, sometimes when the data is very redundant, I get like 1,000-fold compression. And we will have the calibration of the offset of the frequency synthesis offset calibration, online calibration, without having to trigger it or just in specific moments, just by using a SI 5351 with more output, so I can just get one as reference. And this we're already testing. Have analog SSB support in the UI, so one can just grab the phone and press the PTT and talk to any analog radio around, and also listen to analog broadcast. Is useful. And more ahead, Harold again mentioned to me an NCP, node-to-node copy protocol. It's like a UCP, but with cryptography, and it's very interesting. And I still hunting for time to do some trials with NNCP over the air. There are some things I need to solve yet, some shortcuts I took using UCP, and how I'm going to do in NNCP. And concerning our modding, right now we're always using peer-to-peer connection. We plan to have a multiple users capable Mac with adaptive bandwidth, adaptive channel selection, and also in the future synchronous communication, hopefully telephony, digital telephony, or at least be able to bridge a connection. I mean, we will not have in the near future full duplex, but we can have half. And with simple voice activity detection, we could even route a GSM call, one per radio. But with frequency division, we can think even about more than one. And also DRM reception, DRM broadcast. Having a wideband capable radio, we could transmit digital radio mondial, receive it. And it's interesting because there are already receivers around that can receive. And well, just some funny slide like about the mobile HF telephony. There are people doing it. This is a guy in Australia doing mobile telephony in HF. And here's the coverage that he gets with his small vertical antenna and radio in the back. And usually he goes to the sea and step in the salt water, and this really improves the transmission and also the grounding. So he has a ring here in the knee. It's also part of the grounding of the his portable mobile station. So it's, of course, it's feasible. We want to reach this point that we can use on the go. Of course, you can use in a car, on a boat already, but just walking, we also want to have. It's not rocket science. I mean, it's not that easy, but I mean, the military uses it, so it's possible. People already did. Just need to do it. And that's it. Thank you very much. And I hope we can talk a bit now. So I see a question about LEO satellites, right? Um, yeah, this is definitely a challenge because, of course, they are competing in a way with us, but they have also many problems, special political problems right now. And indeed, for example, the Starlink, there are many countries that don't have support for it. Many of them in Africa. We have started talking to an NGO in Africa that works on Africa. They're really interested on the system. And in the end, HF is not only about connectivity, right? It's also about autonomy and independence. Uh, we don't need nobody. I mean, we don't depend on nobody for our networks to work. Of course, right now we're opportunistically routing emails over the web, but if there was no web, we can just keep routing over HF anywhere in the world. And this is also important to some communities to have autonomy in their communications, even if low bit rate. So yeah, I think definitely LEO satellites are a good option. We even consider, for example, having a Hermes gateway in the forest because the interference and the radio, the spectrum in the forest is much more cleaner. There's no interference from nowhere. So having a maybe a Starlink connection in a station in the forest is a possibility. Um, yeah, but I'm not much into LEO satellites. I see another question from Jianjun Jiao. What's the consideration behind the new FDM LDPC fee versus existing HF FDM open source? Um, in the very past, we were using Dream, and Dream is made for broadcast, right? So there is no automatic repeat request. So you're basically always sending a fixed modulation setup, and and I mean, it's not made for stations to communicate, right? And it's very wideband, right? We don't have a mode, a DRM mode that can work with less than 5 kilohertz. There is an implementation called a Han DRM that they modify the DRM code to work in smaller bandwidths, but it's also not doesn't have none of the automatic repeat request logic and everything. We tried to make our system. The first try, indeed, was trying to use DRM, but it didn't quite work. DRM uses very high order, also FDM modulation. I mean, you are meant to use with 100 kilowatt transmitter, or at least with some kilowatts transmitter. So DRM is usually made to pipe more data because you have more powerful in an asymmetrical network like broadcast. You have a lot more power in the transmitter side, which is not our case, right? We work with low power, so DRM is not was not an option. Uh, no, No, DRM, Digital Radio Mondial. It's a ITU recognized standard for digital sound broadcasting. Yeah, and we considered, and considering other HF or FDM open source, we tried all of them. We tried AirDop. We tried Dave's Row OFDM modem. That's now used by Free Data. That's, I think, the best free software option you have right now. And it's not enough for us. They're all made for ham radio community. And we want to have wideband, for example. We want to go like from very low bitrate to high bitrate. And we want to have adaptive channel aggregation. And we want to have all the stuff that in the end, I don't know if we took the best option, but the option we took is, okay, let's write our own, let's hire people to write it. And that's the path we took. And of course, if there was a free software solution like Vara, we would be very happy of just evolve it. But what we have right now, it's nothing like ready to use or that has a good performance. So yeah, this is. Yes, all the remote stations use solar panel, batteries, and we try to keep the power consumption low, connecting the gateway station connecting to the remote not very often, like let's say 2 times per day or 3 times per day. Because usually, the radio sucks much more power when it's transmitting, right? In RX, the motherboard of the Intel core sucks like 1.5 amps, 12 volts, and the radio in RX mode sucks like less than 300 milliamps. And when transmitting, it can suck up to 7 amps, 6 amps, 7 amps peak consumption. So yeah, we recommend a large battery, more than 100 amps hour, at least two of those big 300-watt panels. In the past, we tried to put our system in the same setup that people were using for voice, for analog voice, and of course didn't work. The battery didn't hang, and the solar panel was not enough because SSB voice is really a very optimized system that it's suppressed carrier, right? So just on the high pitch phonemes, the radio will be really transmitting a lot of power. And for example, in the intervals that I'm talking, there's no power being drawn. So SSB voice is hard to compete. So of course we suck much more energy than SSB analog voice because we are not carrier suppressed. Yes, exactly. Up to 75 watts in peaks, right? It's usually when you're transmitting already for some seconds, it will be 4 amps. But we want to have more power in our radio. The next version will have 50 watt of RF power output, and then it will be much more. It will be more than 10 amps of consumption easily. And because in the end, a bit of power is good. And if we can control the power output, we can also see how much power we have in the battery and if we should use more power or not. So this is why we did some work of integrating to the solar controller so we can know more or less where we are in terms of power and how much we can use in the future, right? If anyone want to take the microphone to talk, feel free.
Yeah, so I take the opportunity. So thanks, Rafael, for the talk. So for these communities, how much data do they normally transmit over a course of a day, and how much is this per person, just to get an idea how high the usage is per person?
Well, right now in some communities, people want to exchange like a spreadsheet file with the price of goods, one picture of someone with a disease, or a picture of some loggers invading their land. We made it clear that the data budget is low. So you can send a lot of text messages, but audio and pictures are heavy. And also, like spreadsheets are not heavy, but also not so small when they're big. And we try to make them understand that is to be used like for more or less relevant topics. Um, and now with this work with SMS, we're trying to really attract more people to use the system in the communities. Right now are mostly the people monitoring the environment, making sure there are no invaders and some more vital communication. And the fact is that right now we are using email, right? And many of these people in the communities have relatives in the city, in different cities, in places where there is telephony and internet. But people don't really use much email. Some people don't even know what email is. And so we are thinking in a way to really make the system more useful to them to integrate with SMS. Of course, the first thing people ask is WhatsApp. And I even did some tests with What's Meow. That's implementation that you gives me the QR code, and then I scan the QR code, and then I enable the daemon to exchange messages. So yeah, the system is evolving still, but the usage is still limited. Let's say like this, and the first version of the system also had a bit of hiccups, some hiccups that the most of the hiccups are in this gateway station, that there is too much interference, or people don't like the noise of the fans of the radio, and people forget to turn it on because they turn off at the night. And there are many logistic issues that we're still working with these first communities. I mean, basically, it's one in Rondônia, one in Ecuador, one in Brazil, one in the region of Puyo in Ecuador. And we are working with these two communities to also to learn, right, how it's better to them, and also to try to see how to fix these logistical problems and keep things working. I mean, the gateway station is the heart of the network, so when it's off, people just stay without communication.
So I was curious with these gateway stations, and you may have mentioned this already, but when people connect to them, are they? I guess how do they get their spreadsheets and things like that? Are they logging into an email server hosted on the gateway, and are they polling that locally, or is it more of a push system for them?
Yeah, I mean, the your mailbox is really in your community, right? And all the exchange of email is done by UUCP, and the connections are only originated by the gateway. I mean, only the gateway calls. So there is like a round robin, or how you want. You can set in the interface a scheduler that your gateway will connect to the remote stations once per day, twice per day, and then all these emails with a spreadsheet, for example, will synchronize. I mean, go back and forth, or go to the community, or to the community to the gateway, when the gateway connect to such community and exchange the data and synchronizes the UUCP data. That's where the emails will be, and then they go. So right now it takes some time, I mean, for the email to go. It depends on how you set the system. If you connect to each station every 5 hours, from 5 hours, your emails will go through, let's say like this. And also you receive emails in the other direction. Right?
I see. That makes sense. I guess I was curious in terms of how it will adapt to the SMS use case where people might expect more frequent synchronizations.
Yeah, I mean, right now we are doing this of very long delays because just just for the UCP handshake overhead, it takes 1 minute, 2 minutes, and then to actually exchange the data, many more minutes. And so if you have, let's say, 10 stations and you spend like 40 minutes for each station, the faster you can go back to the first station, let's say like this, is 400 minutes, right? And so each network has a size, and then we need to make this math. That's why we're working on the molding, because if we have a media access control layer that we can have multiple access and multiple users sharing the time, and then it will be much faster. But right now, with all the overhead we have, it works like slowly, and then it's not so fast. But as they say, I mean, if I get a boat, I will take 1 day by boat to arrive to the nearest community. And if the message takes 5 hours, it's better. Of course, we added an option in the UI of the remote station to force the connection. So in the remote station, we left the option for you to try to connect to the gateway to send your data. Let's say in an emergency, it's possible. But of course, this is dangerous because you can cause clashes on air, right? Imagine the gateway station will just be about to call station 2, but then station 1 tries to connect to the gateway, right? So we avoid this by having a plain start topology and just the gateway originates the call. So yeah, it was just the easier way to solve the problem and to really start working without any conflict or any risk of on-air clashes.
Yeah, makes sense. Thanks.